Hello, my name is Lily Chenoweth.
And my name is Caitlin Cordero.
And for our physics project, we were trying to determine the relationship between the final velocity and drag force of a water submerged cube. So we did this by dropping a cube into water, and we wanted to see how the velocity of the cube would change according to Stokes' law.
Right. So for this lab, since we are observing that relationship between the velocity and the force of drag on an object in a submerged liquid, we're using Stokes' law, which is given here. So Stokes' law is specifically used for spheres, and it is force of drag equals 6 pi r for radius, eta times the velocity. However, since we were not using spheres for our equation, we had to alter the Stokes' law equation. So we used that the force of drag equals a constant times the velocity of the falling object. And the reason we were able to do this is because we maintained the radius of our objects and the fluid viscosity, which is given by eta, because we used tap water the whole time. So given that all of these values remain the same, we were able to keep this as a whole constant c, and this was the equation: force of drag equals constant c times velocity in meters per second squared for our Stokes' law expression.
So when we were experimenting, we timed how long it would take our cube once dropped to reach the bottom. So once we had our t, or our time, we needed to plug it into our motion equation, where distance equals 1/2 acceleration times the time squared. So we derived that to solve for the acceleration. And once we had that, we were able to plug it into another motion diagram to solve for our final velocity, which is what we were trying to calculate. So we had final velocity equals the square root of 2 acceleration from our previous equation times the delta t, which we measured on the cylinder. We expected the velocity to change based on the different masses of our cubes, and we also kind of expected to see a relationship between the hydrophilicity of our cubes. So some of the cubes were metals and some were non-metals. We expected the metals to be a little bit less hydrophilic than the non-metals. So we were anticipating to see those move faster, as they weren't as attracted to the water itself.
So in order to find our force of drag that we were looking for, we used the equation force of drag equals the force of gravity minus the force of buoyancy minus the net force. And we were able to account for this based off of the free body diagram that we drew. So here is our theorized mass, and it was falling in a submerged liquid. So because it was falling and its acceleration was going downwards, this is because of the mass times gravity, mass times gravitational constant, which is the force of gravity. And then the opposing forces acting upwards are the force of drag and the force of buoyancy. So the force of drag was given by, the force of buoyancy was given by the fluid density times the gravitational constant times the volume displaced of the liquid. And this was a constant because the volume displaced was just the volume of the cube, and the volume of the cube was the same for all of them, of 0.000008 meters cubed. And so we took the force of gravity here, and then we subtracted the force of buoyancy and the net force, because the gravitational force acting downwards was the main component. So then we were able to subtract these values. And that's how we were able to solve for the force of drag.
For our materials, we used a 1,000 milliliter graduated cylinder filled with water to the 950 milliliter line. And when we had our cube in here, we had to make sure to know how far it was dropping. So we measured it with a meter stick.
We also used a triple beam balance in order to accurately determine the mass of each cube that we used. And in order to determine how long it took to hit the bottom of the graduated cylinder for each fall, we used our phones for a stopwatch. And then, of course, we used these different, same sized cubes, but different materials. So the ones that we used were aluminum, iron or steel, brass, copper, acrylic, PVC, and nylon.
So for our procedure, we had to measure the weight of each of our cubes. We had 7 total. So we used our balance for that. And then once each was recorded, we filled the water up into the 950 milliliter line. And then, as stated in our materials, we measured exactly how far it would drop to use in our calculations on Excel. So once we filled it with water, we had our stopwatch at the ready, and we lined up the very bottom of the cube to the 950 milliliter line where the water was, just to break the surface tension, but not any farther than that. So once the cube was dropped, we started as immediately as it was let go, we started the stopwatch, and then as soon as it hit the bottom, we stopped the stopwatch. This was repeated a total of 4 times for each cube, and we did it for 7 cubes total.
Ready, set, go. Ready, set, go. So using the calculations that we presented here in our theory section, we took our data that we evaluated and we logged into this Excel spreadsheet, and we plugged in our values into the calculations. And so here are some sample calculations and sample values that we had using our data that we collected. So given the results graphs that we have, we were able to use these in order to determine the relationship between the velocity and the drag force. And in order to do this, we used the natural log of these values, and then we graphed them. So when we were doing so, we got a slope of 1.4732, which represents the power of the relationship between the velocity and the drag force. Our expected slope for this graph was 1 because of the direct relationship between velocity and drag force that we were predicting from the Stokes law equation, force of drag equals some constant times velocity. Therefore, when we calculate the error between our expected slope and the actual value of this graph, we get an error of 32.12%.
From our initial graph between velocity and drag force, we see that the graph is pretty linear, which we were expecting. Our R-squared value was 0.9587, so we can conclude there is a direct relationship between velocity of the falling object and the drag force. The slope of this graph was negative 1.5681, which was our C value in our derived drag force equation, where drag force equals CB. This was in place of that initial 6 pi r eta that was used in the standard Stokes law equation. This coefficient C was constant for all of our trials because the displaced volume of the liquid was used. It was the same as each dimension was the same for each cube, as well as the liquid. The y-intercept of this graph was 0.3784, which was systematic error. We expected this value to be 0. So in our experiment, we had a percent error of 32.12%. This most likely came from personal error, such as starting or stopping our stopwatch too early or too late. As well, when we were dropping the cube, it would often hit the sides of the graduated cylinder, which would mess up the time that it fell. As well, it would be spinning. So sometimes it would be spinning faster versus slower, and it would be inconsistent between the trials.
So in order to improve this experiment for future trials, we would recommend using a sphere instead of a cube. That way, the radius would be constant as the object falls, and you could use the given Stokes law equation, force of drag equals 6 pi times the radius of a sphere times the fluid viscosity times the velocity. And we could have used this instead of having to use a derived equation that we did. Force of drag equals some constant times the velocity. We also could have improved this experiment by having a more accurate way to measure time. So we would recommend this by doing more trials, as well as using a sensor to measure exactly when the bottom of an object hits the graduated cylinder. However, we were still successful, despite our errors that we had, to observe a direct relationship between the velocity of a fallen object in a submerged liquid and the drag force. And this confirms Stokes' law.
Thanks.
Thank you.